Understanding soil properties is essential for nutrient planning and can be applied to land use decisions. A soil's properties are largely determined by its parent material and weathering during its formation. Topography, age, and agricultural practices can also affect a soil's properties. It is the combination of various properties that determine soil health and the ability of the soil to provide ecosystem services. Each soil has different types and arrangements of these components which create unique soil properties or soil types. Soil properties influence plant growth and crop decision making. Phases of soil. A soil mass consists of the solid particles and the voids in between them. These voids are filled with air or water or both in different proportions. So, there is a three-phase system, but when the voids are only filled with air or only filled with water, then soil becomes a two-phase system. Three-phase system can be represented with a diagram as shown. When the voids are only filled with water, it is said to be saturated. Total volume of the soil mass V equals VA plus VW whole plus Vs, where V equals total volume, VA is the volume of air mass, VW is the volume of water mass, Vs is volume of solids, but Va plus Vw equals Vv, where Vv is the total volume of voids. So, V equals Vv plus Vs. Properties of soil. Properties of soil can be classified into mainly three classes, namely physical, chemical, and biological properties. Physical properties. The physical properties include texture, structure, and color. Soil texture refers to the particles composing the soil. These particles are classified as gravel, sand, silt, and clay in decreasing order of size. Soil structure refers to the arrangement in which soil grains are grouped together into larger pieces. An individual natural soil aggregate is called a PED. Soil structure is described in terms of the shape, the durability of the PEDs. Major types of structure are blocky, granular, columnar, prismatic, crumb, and platy. Soil structure influences the absorption of water by the soil, its erodibility, and plowing. Soil color is a minor physical attribute, but it is the most readily observed. It indicates the origin and composition of the soil. Increasing quantities of humus produce a range from white through brown to black. Black and dark brown colors are typical of soils in the cool and humid areas of the temperate latitudes. Soil in the steppe lands and deserts are light brown and grey. Red and yellow colors are quite common and both are due to the presence of iron oxides and hydroxides. Chemical properties. Chemical properties of soil include soil water chemical composition, soil colloids, handy humus, and soil air. A soil's chemical composition can be tested only in a laboratory. Some tests for specific purposes, however, such as checking acidity, are routinely done in the field. Soil colloids and cation, ion exchange, acidity and alkalinity in terms of pH are some of the important chemical properties. Biologic processes in soil. The total role of biologic processes in the soil formation includes the presence and activities of living plants and animals as well as their non-living organic products. Living plants contribute to soil formation in two basic ways, namely biomass formation and nutrient recycling. The soil microorganisms can be classified into microflora, namely bacteria, actinomycetes, fungi, algae, and microfauna, namely protozoans, nematodes, etc. Human activity is also a potent agent in influencing the physical and chemical nature of the soil. Soil's texture. Particle distribution. Particle distribution, also known as gradation, refers to the proportions by dry mass of a soil distributed over specified particle ranges. Gradation is used to classify soils for engineering and agricultural purposes, since particle influences how fast or slow water or other fluid moves through the soil. Particle is a fundamental property of any sediment, soil or dust deposit can provide important clues to the nature and provenance. It influences a variety of other properties. As per Indian Standard Soil Classification System, soil is classified into 9 classes based on grain size. The range of the particle encountered in soils is large, from boulders with dimension of over 300 mm down to clay particles that are less than 0.002 mm. The classification as per Indian Standard Soil Classification System is as follows. Very coarse soil. It is subdivided into boulder, which are greater than 300 mm in particle, and cobble, which are 80 to 300 mm in particle size. In some other classification methods, cobble is also called pebble. Coarse soil. Coarse soil is subdivided into gravel, coarse gravel, fine gravel. Coarse gravel, which are 20 to 80 mm, fine gravel, which are 4.75 to 20 mm, sand, coarse sand, which are 2 to 4.75 mm, medium sand, which are 0.425 to 2 mm, fine sand, which are 0.75 to 0.425 mm. Fine soil has silt, which are 0.002 to 0.75 mm, clay, which are less than 0.002 mm. Gravel, sand, silt and clay are represented by the group symbols G, S, M and C respectively. Physical weathering produces very coarse and coarse soils. Chemical weathering produces generally fine soils. Textural classes. Texturally, soil is classified into 3 classes, namely sand, silt and clay. Some soils are fine while others are coarse. It is so because of the fact that the relative percentage of sand, silt and clay differ from soil to soil. The relative percentage of soil separates of a given soil is referred to as soil texture. Texture of the soil for a given horizon is almost a permanent character because it remains unchanged over a long period of time. Soil is further classified into 9 more classes based on the proportion of sand, silt and clay as loamy sand, sandy loam, sandy clay loam, sandy clay, medium loam, clay loam, silty loam, silty clay loam and silty clay. These extended classes are discussed in soil triangle. Sand. This fraction of soil consists of loose and friable particles of 2.203 to 0.02 mm diameter. Sand particles can be seen by unaided eye. These particles, although inactive, constitute the framework of the soil. They play less important role in physico-chemical activities. When coated with clay, these sand particles take very active part in chemical reactions. Sands increase the pore spaces between the soil particles and thus facilitate the movement of air and water in the soil. Silt. It consists of soil particles of intermediates between sand and clay, the diameter range being 0.02 to 0.002 mm. Silt when wet feels plastic, but in dry state feels like flour or talcum. Coarse silt shows little physico-chemical activities, but finer grades play important role in some chemical processes. Silty soil has got larger exposed surface area than the sandy soil. Silty soil contains sufficient quantities of nutrients, both organic and inorganic. That is why they are very fertile. Soils rich in silt possess higher water holding capacity. Such soils are good for agriculture. Clay. This soil fraction contains smaller particles than silt, that is less than 0.002 mm in diameter, which exhibit plasticity and smoothness when wet and hardness when dry. Owing to their smallest and colloidal nature, the clay particles expose extremely large surface area. They take very active part in physico-chemical reactions of the soil. Clay soils have fine pores, poor drainage and aeration, and thus they have highest water holding capacity. The clay acts as a storehouse for water and nutrients. Textural triangular diagram. FAO and UNESCO has recommended a triangular plot to identify the texture of the soil when there are exactly 3 variables. Triangular diagram is also called ternary diagram. In the graph, soil composition can be determined using the 3 variables. If we know the percent sand, clay and silt, we will be able to determine exactly what kind of soil we have. In addition, if we want to make silty clay loam, we would know that we need 60% silt, 25% clay and 15% sand. All three percentages add up to 100%. Description of the triangle. Triangle's base represents sand percentage from 0 to 100, increasing from left to right. Left hand side slope represents percentage of clay increasing from bottom to top, and the third arm, the right hand side slope, represents percentage of silt increasing from top to bottom. The inside area is divided asymmetrically into 12 parts, namely sand, silt, clay, loamy sand, sandy loam, sandy clay loam, sandy clay, medium loam, clay loam, silty loam, silty clay loam, and silty clay. How to use the ternary diagram? Assume that the given soil sample has only 3 components. Estimate the percentage of clay, silt, and sand in the soil. The 3 percentage values must add to 100%. Let us take an example that the given sample has 60% silt, 15% sand, and 25% clay. On the right hand side silt arm of the triangle, mark a point at 60% and draw a line downwards towards sand arm parallel to clay arm. On the bottom side sand arm, make a mark at 15% and draw a line upwards clay arm, keeping the line parallel to silt arm. Finally, on the right side silt arm, make a mark at 25% and draw a line towards silt arm, keeping the line parallel to sand arm. Now, we can see that all the 3 lines intersect in one point. In this example, we can see that the intersection point lies in the area of silty clay loam. Therefore, the given sample is silty clay loam. Significance of soil texture. It influences physical and chemical properties like water holding capacity, nutrient retention and fixation and its availability, drainage, strength, compressibility and thermal regime. Suitability of a soil to a particular crop depends on texture in addition to soil depth, depth of the water table, salinity and alkalinity. Loamy soils, silty, exhibit intermediate properties, so best for agricultural production because they retain more water and nutrients than sandy and have better drainage, aeration and tillage properties than clay soils. Soil structure. Soil structure refers to the arrangement of soil particles, namely sand, silt and clay, and pores in the soil to the ability of the particles to form aggregates. Aggregates are group of soil particles held together by organic matter or chemical forces. Pores are the spaces in the soil. The pores between the aggregates are usually large. Macropores. Their large allows good aeration, rapid infiltration of water, easy plant root penetration, good water drainage, as well as providing good conditions for soil microorganisms to thrive. The smaller pores within the aggregates or between soil particles, called micropores, hold water against gravity, capillary action, but not necessarily so tightly that plants cannot extract the water. Classification. By definition, class of structure describes the average of individual aggregates. Usually, 4 distinct classes based on the thickness or thinness of the aggregates are 1. Granular, 2. Blocky and subangular, 3. Prismatic and columnar, 4. Plates or platy structures. Granular and crumb structures are individual particles of sand, silt and clay grouped together in small, nearly spherical grains. Water circulates very easily through such soils. They are commonly found in the A horizon of the soil profile. Blocky and subangular structures are soil particles that cling together in nearly square or angular blocks having more or less sharp edges. Relatively large blocks indicate that the soil resists penetration and movement of water. They are commonly found in the B horizon where clay has accumulated. Prismatic and columnar structures are soil particles which have formed into vertical columns or pillars separated by miniature but definite vertical cracks. Water circulates with greater difficulty and drainage is poor. They are commonly found in the B horizon where clay has accumulated. Platy structure is made up of soil particles aggregated in thin plates or sheets piled horizontally on one another. Plates often overlap, greatly impairing water circulation. It is commonly found in the forest soils in part of A horizon soils. Soil consistence. Soil consistence is defined as the resistance of a soil at various moisture contents to mechanical stresses or manipulations. It combines both the cohesive and adhesive forces which determine the ease with which a soil can be reshaped or ruptured. Soil consistence is described at 3 moisture levels, namely wet, moist and dry. The gradual increase in water content causes the soil to change from solid to semi-liquid to plastic to liquid states. The water contents at which the consistency changes from one state to the other are called consistency limits or Atterberg's limits. The 3 limits are known as the shrinkage limit Ws, plastic limit Wp and liquid limit Wl. Cohesion, adhesion and plasticity. Cohesion is the attraction of one water molecule to another resulting from hydrogen bonding. Water-water bond. Adhesion is similar to cohesion except with adhesion involves the attraction of water molecule to a non-water molecule. Water-solid bond. Plasticity is the degree to which puddled or reworked soil can be permanently deformed without rupturing. Evaluation of plasticity is done by forming a 4 cm long wire of soil at a water content where maximum plasticity is expressed. Atterberg's constants. The Atterberg's limits are a basic measure of the critical water contents of a fine-grained soil. Its shrinkage limit, plastic limit and liquid limit. As a dry clayey soil takes on increasing amounts of water, it undergoes distinct changes in behavior and consistency. Depending on the water content of the soil, it may appear in 4 states: solid, semi-solid, plastic and liquid. In each state, the consistency and behavior of a soil is different and consequently so are its engineering properties. Thus, the boundary between each state can be defined based on a change in the soil's behavior. The Atterberg limit can be used to distinguish between silt and clay. Upper and lower plastic limits. The liquid limit represented by LL. The percentage moisture content at which a soil changes with decreasing wetness from the liquid to the plastic consistency or with increasing wetness from the plastic to the liquid consistency. The plastic limit represented by PL is the percentage moisture content at which a soil changes with decreasing wetness from the plastic to the semi-solid consistency or with increasing wetness from a semi-solid to the plastic consistency. Plasticity number. Plasticity numbers are the index numbers denoting degree of plasticity of the soil based on the plastic limit in percentage. Degree of plasticity is divided into 6 classes under 3 categories: 0, 1, non-plastic, sand or silt soil; 1 to 5, slightly plastic, sand or silt soil; 5 to 10, low plasticity, sand or silt soil with traces or little clay; 10 to 20, medium plasticity, clay loam; 20 to 35, high plasticity, silty, clay soil; more than 35, very high plasticity, clay soil. Soils from 0 to 10 are considered as category 1, soils from 10 to 20 under category 2 and more than 20 are considered under category 3 soils. Summary. A soil mass consists of the solid particles and the voids in between them. These voids are filled with air or water or both in different proportions. The proportion of different media results in different phases of soil. These phases influence the properties of soil, which can be classified into physical, chemical and biological properties. The main physical properties include texture, structure and color. Texture of soil is classified into 12 classes based on the relative proportion of sand, silt and clay. These are represented in a textural triangle diagram. Soil consistence is defined as the resistance of a soil at various moisture contents to mechanical stresses or manipulation. The Atterberg limits are a basic measure of the critical water contents of a fine-grained soil. Its shrinkage limit, plastic limit and liquid limit. Plasticity numbers are the index numbers denoting degree of plasticity in the soil based on the plastic limit in percentage. The study of these properties help in understanding the soil better.